Well, really, thank you, Kavita, and also all of the local staff and organizers for making this possible. Jessica, Luigi, it's really a pleasure to be here at my first in-person workshop talk since COVID began. So this will also follow up nicely with Peter's talk this morning. This is in the same genre, which I think is a very interesting new direction in mean field game theory, with a lot of open problems and questions remaining to be answered. This direction being kind of moving past this key sort of homogeneity premise behind mean field game theory. So before I get into things, let me mention this is all based on a joint work with Agathe Soret, my PhD student, who was an integral part of all of this, but is maybe not here to help me answer questions, unfortunately, on short notice. All right, what's the premise here? Well, this is a mean field game workshop. I think many of us know by now that mean field game theory has been really widely successful in a lot of applications. It is a very rich mathematical theory, but the key, really, the mean field part, this term mean field, essentially refers to this assumption that agents are interacting symmetrically with each other. Everyone interacts equally with everybody else. Now, that's not to say players are completely, homogeneous. Economists call these heterogeneous agent models because each player has their own individual data, like their own independent random source of noise, maybe also some random type parameter assigned to them. But what we're trying to push past here is the homogeneity of the interactions. So we want to allow different players to have different strengths of interactions. And a natural way to think about this, as we saw in Peter's talk this morning, is to imagine that maybe we have n players and they are labeled, they're named by the vertices in a graph. And the edges between the players, between these vertices, dictate who interacts directly with whom. So Peter's setting works more generally with really some kind of interaction matrix, where the matrix at entry ij dictates the strength of interaction between the players labeled I and j. Here, I want to think of even more simply that we just have a network and everyone's going to interact symmetrically with their neighbors in the network. The mean field case being recovered by looking at the complete network where everyone's connected. Okay, so this is what we want to try to do here. I'm going to focus on a case study, a very simple model where we can do things kind of semi-explicitly to try to get a sense of, what is the influence of the network? What are the range of kind of possible things that can come up with different network structures? And two more concrete, slightly more concrete questions that I'll make even more precise. First is, when can we still get away with the usual mean field game approximation, right? If we take some large collection of players and they're all connected with each other, except maybe me and Kavita got in a fight and we're not talking anymore. If you remove one edge from a very large network, the mean field approximation that we know and love should still work. And more generally, kind of what is the range, how robust is the mean field game approximation to perturbations like this? And then the second natural follow-up question is, okay, if we're in one of these cases where the usual mean field game model is not a good approximation, then what should we do instead? Is there some alternative limiting model? And this graph on business gives one answer to this second question, which I'm not really going to get into here. More, I want to present this case study that illustrates kind of a range of phenomena that can happen for different kinds of graph structures. Now, I want to also highlight that I hope this talk will be accessible to the non-mean field game experts in the room. This is really a case study. There's plenty of reference to mean field game theory, but hopefully the model is concrete enough that we can understand it without too much expertise. So what is the model setup? It'll fit in this one slide here. There's a finite graph given to us, and I want to set up this model on any finite graph that you might give me. So if we start with some finite graph, the two bits of notation I'll need for these graphs are the degree and this tilde symbol, which will mean that they're connected. The degree means how many neighbors does this vertex have. And now each player in this game is going to be labeled by one of the vertices of this graph. And otherwise, it'll be kind of, they'll be following the sort of simplest dynamics that we see in mean field game theory, where each player just controls some drift added to an independent Brownian motion. For simplicity in the talk, we'll all start at position 0 as well. And to be concrete, let me mention we're going to work with Markovian controls here, where each player is picking a function that they're kind of reacting to the whole network, what everyone else is doing in the model. Okay, and now all of the action in this model is going to come in this cost function here. So in the running cost, we have a very simple standard quadratic running cost, an energy term, let's say. And really all of the business is in this terminal cost that tells us that each player wants to be close to the empirical average of the neighbor's positions at the final time. So we have some fixed amount of time, say 1 day. And at the end of the day, I want to be kind of close to where my buddies are. Maybe this X represents your opinion and you want to kind of agree with your friends on average. This fits into a broader kind of realm of so-called flocking models where players or whatever you think of your players as tend to attract together toward each other. Okay, so this constant C here controls the trade-off between these two terms, how strongly you want to be close to your buddies versus minimize your energy to get there. Okay, what else should I say about this? As usual in this game theory business, we want to look for a Nash equilibrium, which I have not put a definition of on the slides, but I hope this is clear. And to say a bit more about motivation here, the reason I like this kind of model comes from the fact that it should be tractable. It should be kind of solvable. If you replace this whole blue term with some general function of the positions at time capital T, and if we instead have just one single player instead of a bunch of players, then this is a very classical, simple kind of control problem that has basically an explicit solution. This is the Kohlhoff solution, basically. So we'd hope that by going to the n player setting, but keeping this kind of simple structure, this quadratic running cost plus a terminal condition, this should be sort of reasonably tractable. Turns out we'll only have explicit solutions in fairly specific graph structures. So that'll be kind of the second half of the talk. But for now, this is the basic model setup. To say a bit more about maybe for those who are not MFG enthusiasts already in the room, one thing I find very interesting about these models from a probabilistic perspective is that you can start with something very simple looking like this, like we're interacting with the average of our neighbors. But as we'll see as we go along, the equilibrium, this process of Nash equilibrium kind of mixes together all of your randomness in more complicated ways that are kind of hard to disentangle sometimes for probabilistic limit theories, right? Like we all start with our independent noises, but then we're going to depend on each other after we resolve the Nash equilibrium. Our controls are going to depend on each other. So this is where kind of the challenge comes in from a probabilistic perspective, you might say, if we want to understand large scale models like this. Okay, so this is the setup I'll be focusing on for the whole talk. So just to give a little more, the benchmark case will be this mean field case where we take the complete graph on n vertices. So everyone's connected with everyone, and the large scale asymptotics are extremely well understood by now for this model. So I'll summarize some of it here because we'll need a bit of it as we go on. This n-player game, Markovian Nash equilibrium, can be computed explicitly. The precise form is not super important. It's just some time-dependent constant times the average of everyone's position minus my own position. So I move toward the average with some speed that kind of increases as we get closer to the final time horizon. I kind of push harder when the clock is running out. It's completely explicit though. You can solve the corresponding mean field game, which I'm not going to write down what this mean field game fixed point problem looks like. Charles, your question?
Can you pass on this?
Thanks. How can you ensure that there is a unique solution in this case?
Oh, I'm not claiming uniqueness.
Okay.
Yeah. I hope I didn't say unique.
No, but you mean like the solution, so
this is probably unique, but uniqueness is sort of a harder thing to prove in these n-player stochastic differential games with unbounded coefficients and everything. So we're not addressing the problem of uniqueness, which surely I'm sure it is. I'm almost certain it's unique, but this is a bit tangential from the things we want to investigate. So we didn't make any claims as to uniqueness. This you can kind of just prove by an ansatz in the Hamilton-Jacobi-Bellman equations, the n-player PDE system that corresponds to this game. So likewise, this is an equilibrium for the mean field game that I've written below that you can sort of formally derive from the first one if you believe that the empirical average should converge to 0 for large n. And then we're just detracted towards 0. We kind of all mean revert towards 0, again, with this time-dependent speed multiplied by my position. Okay, so this model is kind of inspired by this other sort of flocking type model listed at the bottom of the page here. But what else can we say in this setting? We can say, well, we can also compute the law, the state process behavior, right? This is just a linear control. So when we plug this in to the SDE, we end up with an Ornstein-Uhlenbeck process, basically. And its law is Gaussian. You can explicitly compute the mean and variance. The mean is just 0 because we started at 0. And now in terms of these things that I've told you that I hope you believe me on, we can say a lot about the convergence, which is more the thing I want to focus on for this talk. How do we connect the large scale finite game to some limit? And what you can show, the kind of standard theory in mean field game that you can check by hand in this example, consists of several different statements. First, you can say that a typical player, the law of the state process of a single player is going to converge to this Gaussian. Now, because this graph, we're on the complete graph, everyone's completely exchangeable, I can safely talk about a typical player. Everybody's going to behave the same marginally, and everyone's going to converge to this Gaussian law mu. The empirical measure, the random empirical measure formed by all of these state processes will also converge to this mu. There's also an asymptotic independence. If we pick two distinct players, then they're going to be close to independent to IID with this law mu. And there's also, historically, this kind of came first. The easier way to connect your mean field game to your n-player game is to use the former to build an approximate equilibrium for the latter. So you take the mean field control and you tell player I to just plug in their own position xi into the x position for that mean field control. So everyone behaves independently, just looking at their own state. And this gives you an approximate Nash equilibrium with epsilon being order 1/√n. And so I like to give this example in a PhD course I taught on mean field games. It's a situation where you can explicitly solve the n-player game and the mean field game and really verify that everything works by hand without having to, prove difficult theorems about non-explicit objects. So this is a good kind of benchmark case, this example here. This also motivates the kinds of things we want to look for in a more general setting. So now let's move beyond the mean field case. Let's say that I give you now a sequence of graphs. I give you some large graphs, and I want to try to answer the same kinds of questions. Now, the model I set up at the beginning can be run on any graph you give me, right? So this makes sense to now think of a sequence of growing graphs and ask for basically the same kinds of things here. Can we say that, can we identify limits for a typical player, the empirical measure? Is there some form of asymptotic independence here? Is there some way we can construct approximate equilibria in a similar way? Can we still use the mean field solution, even though we're not on a complete graph anymore? And will this still give us a good approximation? These are the four main questions I'll answer in this talk. I don't have an answer yet to 5. If there's, if the mean field solution doesn't really work, there's not really an alternative limiting model yet, at least in the sparse graph case, the graphon business covering the dense graph regime. But first of all, we need to already be sort of careful about formulating some of these questions. This first one in particular, as I mentioned, when we're on a general graph, players are not exchangeable. So what do I even mean by a typical player? And normally I'll mean, let's pick one player at random and see what they look like. So this will be how I think of a typical player. Okay, so just a bit of intuition here. There's a big difference between the sparse and dense cases I just mentioned. And this is kind of something you see a lot of if you read about the literature on interacting particle systems on graphs, on lattices, but also on more complex networks that have been studied. You expect that on kind of sufficiently dense graphs, certain mean field sorts of arguments will go through, but in more sparse settings, there are different phenomena usually. And the intuition behind that is that the pairwise interaction strength is 1 over the degree. So if you have more and more neighbors, then you'd expect to kind of decorrelate with your neighbors. Agathe.
Question, when you say sparse, are you talking about little o of n where the graphon model doesn't work, or you're talking about where the degrees are actually asymptotically bounded? Because both are used sometimes.
Right, good question. I'm being a little vague here about dense and sparse. There are different sparsity thresholds that we'll see for different kinds of phenomena, which relate to how many edges there are relative to the number of vertices. So I'm going to stay vague about this for now. Yeah. Okay, so before I get into things, let me just mention briefly that, and this talk was prepared on short notice, so the reference list is a bit dated by now. There's been a lot of progress in the past year or two, even as Peter discussed some of this morning. In the game theory literature, there's been some work on these graphon-based models, which are very much focused on the dense regime and can so far focused mostly on this, as Peter's talk was this morning, on identifying a limiting model and then constructing your approximate equilibria from that. And I'm trying to focus more in this talk on this perspective of starting from our n-player model and identifying, seeing where that converges in a sense. But there's been more and more work in these graphon games, but also some other case studies on particular graphs. Francois was one of the first to this business to study a model on the Erdos-Renyi graph in the dense case, where P is fixed as n converges to infinity, and there you do have a mean field behavior. J.P. Fook and Tomoyuki Ichiba and various students of theirs have studied models on the kind of most sparse graph you can imagine, where you have a bunch of players connected in a cycle, maybe a directed cycle even. And you let n go to infinity there. And the cycle enables, so the directed cycle enables some very kind of nice explicit constructions. But we're trying to focus on a broader set of graphs than just the cycle here. And I think I'll skip quickly over this, but there's kind of analogous work you could imagine on interacting particle systems without any game theoretic component, both dynamic and static sorts of interacting particle systems. Both in dense and sparse regimes. So there's some precedent, but the kind of game theoretic versions of these models are more recent. Okay, so before I get into any results, let me remind you of the basic setup, which was that if you give me any finite graph, we can set up this game where the players are the vertices of this graph. We all control our state process. And again, the most important thing here is this cost function where we minimize the quadratic running cost and this terminal cost that tells us we want to be near the average positions of our neighbors. And I will occasionally want to allow an isolated vertex that has no neighbors, in which case let's just set this average to be 0 by convention. That'll be convenient at 1 or 2 points later on. So there are kind of two main results I want to discuss that take different perspectives on the limit theory, let's say. And the first is, the title's cut off at the top here, but the first set of results is about using the mean field game control, the mean field game solution to construct approximate equilibria, even though we're not in a mean field, we're not on the complete graph anymore. So this alpha MF is as before, it's this exact same control we would get by setting this game on the complete graph and looking at the mean field limit. And now let's just say we're on some finite graph G. This will actually be a non-asymptotic statement I'm going to put here first. So let's just say we're on some finite graph and we want to just all use this control anyway. Let's just try it and see how it goes. And what turns out is we can bound the kind of error incurred by each player. How far from equilibrium are we? And it's natural here to take an error, this epsilon, depending on which player we are, because things are asymmetric here. We're not going to demand a uniform epsilon bounding the errors of all of the players. What we have here is that this particular epsilon, which is a constant over the square root of your degree, this collection of epsilons gives you an approximate Nash equilibrium in the sense that if we all use this mean field control, and if we all commit to using this mean field control, then one player, let's say V, tries to switch controls to improve their cost, they're not going to improve their cost by any more than this constant epsilon V. Okay, so this is a non-asymptotic statement. This model is explicit enough that we can say something this concrete, this explicit. But you can easily from this derive various asymptotic statements, right? If we now want to take, instead of a fixed graph, a sequence of growing graphs, then it's kind of obvious that the condition you want in order to ensure that this mean field approximation works is that the degrees are going to 0. But the precise sense in which the degrees go to 0 will determine the precise notion of approximate equilibrium that we have. And this is maybe the first punchline of this talk, is that when we move to these graph settings, we should adapt and be a bit more flexible in our notion of approximate equilibrium compared to the canon of mean field game theory. Okay, so a first example here, the epsilon definition is recalled at the top. The first kind of simplest class of models would be those for which we have a sequence of graphs with diverging minimal degree. So this delta is the minimum degree over all of the vertices. This is the who has the fewest neighbors in the whole network. And if this goes to infinity, then this previous non-asymptotic theorem tells us that we have the mean field game solution gives us an approximate equilibrium with this epsilon and approximation in the usual sense that we have the same epsilon for every player. And this epsilon is order 1 over the square root of this minimal degree, which matches the order 1 over root n in the mean field case, in the complete graph case. Now, if we think more concretely, what's an example where this minimum degree diverges? The Erdos-Renyi is a good benchmark case. This covers the Erdos-Renyi graph when NP, the average neighborhood size, is growing faster than log n. This is actually the threshold for connectivity of an Erdos-Renyi graph. So if NP grows more slowly than log n, there will be isolated vertices with high probability. So we can't expect the minimum degree to diverge in that case. Okay, so this covers basically Erdos-Renyi in this NP bigger than log n case. That's where we can use the usual mean field game construction and get an approximate equilibrium in the usual sense. But if we're willing to, relax to enlarge this sense of epsilon equilibrium, allow the epsilon to depend on the player, we can get away with a lower sparsity threshold. This is a kind of second example, right? What's a kind of natural alternative to demanding that the epsilons are going to 0 uniformly is to just demand that they go to 0 on average. Okay, so if we just want the epsilons to go to 0 on average, then all we need is the average of 1 over root degree to go to 0. And this is much more forgiving. This holds for Erdos-Renyi graphs as long as the average neighborhood size diverges at any rate. Okay, so the sparsity threshold that you get for your epsilon equilibrium construction depends on the precise notion of epsilon equilibrium that you're willing to work with. Another way of formulating this kind of epsilon on average goes to 0 is in terms of what some authors have called an epsilon delta equilibrium. So you can say equivalently that for any epsilon and delta positive, there is large enough n such that no more than a fraction of delta players have an error of more than epsilon. So there may be some players that can really improve their cost by switching strategies, but very few players can do so. Either that or very few players can improve their cost by much. So this is a reasonable alternative notion of approximate Nash equilibrium that lets you get again to this better sparsity threshold here. Okay, so this is kind of the first main result. This seems to hold more generally beyond this linear quadratic model as well. And let me mention lastly that if you don't have the average neighborhood size diverging, this will fail completely. If the NP, the neighborhood size, converges to a finite constant, then the typical degree will converge to a Poisson random variable. It will not diverge, and this epsilon equilibrium construction will not work. So this is really a hard barrier. You can't expect this mean field approximation to work if your neighborhood size is not diverging in some sense. So this extremely sparse or sometimes called diluted regime where the neighborhood size stays bounded, this is a different can of worms where different things should come up. Okay, so this is kind of the end of main result number 1. Before I get into number 2, this is a good place to pause if there are any questions. So this is this kind of visiting this classical construction of approximate equilibrium, but in this graph theoretic model. The second set of results I want to present has to do with actually computing exactly the Nash equilibria for the n-player game and passing to the limit from there. So this is in the context of the mean field gain problem, this is called the convergence problem. This is understood by now to be typically much harder to pull off than this construction of approximate equilibrium. Unless of course you have explicit solutions available to you, which is how we'll do it here. That said, our n-player game model, we cannot explicitly solve on a general graph, even though this looked pretty simple at the beginning. There's linear-quadratic. A linear-quadratic model you can turn into a system of Riccati equations typically, but these are not always explicitly solvable. What we are able to do is explicitly solve our model for certain kinds of graphs, for symmetric enough graphs. Okay, so this turns out to be the class of vertex transitive graphs. It's very convenient for us. I don't assume any of you have heard that term before, so I won't explain what kind of models we're working with and then the results we have there. Okay, so I want to explain first what a transitive graph is and why this is very useful for us. And this is just the idea of a transitive graph is just a graph that kind of looks the same from everyone's perspective. So if we're all in a circle, the cycle graph is a transitive graph because, to each of our perspectives, we're just somewhere along a big circle. But let's say, if we add kind of one branch sticking off of that circle, this is no longer transitive because you can either be on that branch or not, and the graph looks different to you. And the way this is formalized is just using, in terms of the automorphisms of the graph, an automorphism being an edge-preserving bijection. And a transitive graph is one for which any pair of vertices has an automorphism that maps one vertex to the other, which means you can relabel the graph to put vertex u at vertex v's position. Okay, so you typically think of it, as I said, this graph looks the same from everyone's perspective. And in particular, transitive graphs are always regular. Everyone has the same number of neighbors. So this is a pretty stringent family of graphs, but reasonably rich to encode a collection of examples that I'll come back to in a little while. The two main ones to think of, as I just mentioned, first would be the complete graph at one extreme, which is transitive, and the automorphisms of the complete graph are any permutations of the vertex set. Any relabeling of the complete graph will give you the complete graph. For the cycle graph, you can't just use any permutation, you can only use the rotations or reflections. Okay, so the automorphism group of the cycle graph is smaller, but it's still transitive. You can still rotate enough to get from 12 o'clock to 3 o'clock, let's say. Okay, so these are I'd say the two main examples to keep in mind, the dense one and the sparse one. But the key assumption for us will be transitivity that lets us solve our model explicitly. And the reason, I guess, these automorphisms play such an important role, and this is a good time to use the board for a moment. The symmetries of the graph really translate directly into the symmetries of our equilibrium, right? So in the complete graph case, in the mean field case, we have exchangeability, which means that if we take our collection of state processes in equilibrium and we, let's say, permute all of the vertices arbitrarily, then these will be equal in distribution. In general, for one of our graph-based models, this will only hold for automorphisms, for relabelings of the graph that respect the vertex structure, the edge structure of the graph. Okay, so if you relabel the vertices with an automorphism, then your relabeled players still are solving the same kind of game, and you can argue that at least if you have a unique equilibrium, this sort of partial exchangeability will hold. And having vertex transitivity is exactly the condition that tells you that everybody's one-dimensional marginal will be the same, right? Because there is some relabeling that maps u to v, that makes the root u become v instead. So this is where transitivity is very convenient. It tells us that even though these guys aren't exchangeable, say the two-dimensional collections of players may not be equal in distribution, but all of the one-dimensional marginals are going to be the same, which is very convenient. Now we can again safely talk about a typical player without any ambiguity, because all of us will be the same in our individual behavior in law. Okay, so this is going to be very convenient, and this will let us sort of reduce things to a one-dimensional system in a sense. Yeah, back to the slides here. Okay, so before I give you any results, let me introduce a small bit of additional terminology. First is the adjacency matrix of a graph, which is pretty standard. You label the rows and vertices, the rows and columns of your graph by the vertices, and you put a 1 or a 0 depending on whether they're connected or not. More relevant for us is the so-called random walk Laplacian matrix of the graph, where you have a -1 along the diagonal, and you have 1 over the degree. If in row V, you have 1 over the degree of V if you're connected to the other vertex. So this is exactly this is the rate matrix of the continuous time random walk on this graph. Now this shows up for us because our terminal cost function can be written exactly in terms of this matrix. When we have the average over your neighbors minus your own position, this is exactly this matrix L hitting the vector X of states. And then you look at the Vth component, let's say, to get player V's cost function. Okay, so this matrix is very relevant for us. In the regular graph case, it's just the rescaling of the adjacent matrix by 1 over the degree. You subtract the identity matrix. Minor comment here for later is that all the eigenvalues of this matrix are real and between -2 and 0. Okay, so this will be convenient in a moment. So the first main theorem here is a description of the solution, the equilibrium of this game. Again, I don't know if it's unique, but this is an equilibrium for this model. On any finite transitive graph, this will work. So the way you build your equilibrium is first by solving a one-dimensional ordinary differential equation, where you take this function q, which is the normalized characteristic polynomial, basically, of this Laplacian matrix. But you take a 1 over root n power up there. And the spectrum of L is negative. So for positive x, this matrix is always invertible. Anyway, you take the derivative of this q and basically use this q as a kind of gradient flow, let's say. You solve the ODE, f prime equals cq prime of f. Remember, c is the constant in front of the terminal cost that controls the trade-off between the quadratic energy and the terminal cost. So we solve this ODE, and once we have the solution, we define a matrix valued function p of t. Don't worry about the precise form. This is just something explicit in terms of this Laplacian matrix L and this function f we just solved. And then we use this to construct Markovian controls. We multiply the state vector x by this matrix p, and look at minus the Vth component to see what player V should be doing. Okay, so this looks a bit complicated maybe, but it's really, everything's completely explicit up to the solution of this scalar ODE. And this is another place where you notice that in general, the controls in equilibrium are not local. The behavior of player V doesn't just depend on their neighbors, even though the cost function just depends on their neighbors. Player V's control depends on everyone. This matrix P will have non-zero entries, I think, all the time. So this is another kind of challenging feature of these graph-based models, where even if you start from these local, these neighbors, nearest neighbors interaction, your equilibrium control will look at the entire network. The intuition, I guess, being that, in a game theoretic setting, I know that my players, my neighbors are looking at their neighbors. So I don't just want to base my strategy on my neighbor's behavior. I want to anticipate how they're going to depend on their own neighbors, and so on and so forth. So this leads to controls which depend on everybody. Okay, so you can write down, the state process. This is all well and good. This is a kind of explicit solution, but it's not obvious immediately here. I think that you can, say anything that you can take limits easily from this kind of solution, right? If we have a larger graph, we have a larger matrix here, and how do we understand the behavior of a single player? It turns out we can take limits pretty conveniently with this if we adopt the right perspective. So this is the next theorem I want to show you. The key observation is that if we're only interested in kind of average quantities and typical player quantities where we pick a player uniformly at random, then all of these quantities can be represented in terms of the spectrum of this Laplacian matrix. Okay, so more specifically, if we form the spectral measure, so we take the eigenvalues of this Laplacian repeated by multiplicity, and we form their empirical measure. Then basically everything of interest on the previous slide I claimed can be written in terms of this measure here. So first I'll try to explain how, then I'll explain why this is useful. So first of all, this ODE was f prime equals CQ prime of f. The function Q is this normalized determinant, which we can then write as a geometric average over the eigenvalues. And if we take an exponential and a log, we can write this as an integral in terms of an integral with respect to this eigenvalue measure here. Okay, so this is convenient manipulation one that makes this measure mu g appear. So this ODE can be written in terms of this function Q, which actually just is determined by the mu g here. Okay, now similarly, if we look at our state process in equilibrium, which is a kind of multivariate Ornstein-Uhlenbeck process, we can write explicitly what's the covariance matrix, and I took mean zero by starting at 0 for simplicity. We can write explicitly in terms of this Laplacian matrix, what's the covariance matrix of this n-dimensional process X. And if we want to take limits here, we can take advantage of transitivity. So if we want to take a limit of a Gaussian with mean zero, we just need to figure out where the variance goes, basically. So if we look at one typical player, then by transitivity, the one player is the same law as each other player. So the variance of one guy is the same as the average of all of the variances. The sum of the variances is exactly the trace of the covariance matrix. And so we get this normalized 1 over n times this trace. And the trace of this complicated functional of the matrix L can be expressed just as an integral or a sum over the eigenvalues or an integral with respect to this measure mu g again. Okay, so everything's written in terms of this mu g, which tells us we can take limits basically if this mu g measure is converging, which is now a property of the graph. Okay, so the next theorem I'm going to show you basically says that if we're given a sequence of graphs with the property that this eigenvalue measure converges weakly to something, then we can describe, we can say a lot about the limiting behavior of this Nash equilibrium that I described before. Before I state this result, I want to explain why it's not unreasonable to make this an assumption of the theorem that this eigenvalue measure is converging. Basically, I want to give you some examples. So the first, let's again start with the extreme case of the complete graph, where the eigenvalues you can compute explicitly for this matrix L. You have what, a 0 eigenvalue with multiplicity 1, and then minus n over n minus 1 with multiplicity n minus 1. So you get this empirical measure of the eigenvalues that converges quite clearly to a delta at -1. This Laplacian matrix, remember, had all -1s on the diagonal. So if we take the normalized trace, let's say, we always get -1, which tells us that the mean of one of these mu g measures is always going to be -1. So if it's going to converge to a delta, it has to be a delta at -1. And more generally, actually, you can show for transitive graphs that this mu gn will converge to delta -1 if and only if the degree diverges. Okay, so in this transitive case, this is really the dense setting. If the degree diverges, this means the variance of this eigenvalue measure is going to 0. These are the same things here. Okay, so this is a kind of useful reference case. And in this delta -1 case, the limits are all kind of very simple objects, as we'll see. And it's the sparse case where we have more complicated things appearing. So if we look at the cycle graph, for instance, this is a circulant matrix that you get for this L, and you can again compute the eigenvalues explicitly here. And the limiting measure is a kind of an arcsine law type thing. You have I think that's what this would be called, the law of cosine of a uniform, basically. And if you want something more complicated, you can take the torus, the lattice, let's say, which has a similar sort of limiting arcsine type distribution, but we have an average of independent cosines of uniforms here. So these are some cases where this eigenvalue measure is tractable, and it does have a limit that we can compute. So this is a reasonable kind of perspective on this. There's a reasonable assumption to make that this eigenvalue measure is converging. So with these examples in mind, the next theorem is then, okay, if we have a sequence of transitive graphs that's growing, let's say, and we assume that these eigenvalue measures are converging to some limit, let's call it mu, then we can describe all of the limits of quantities from our n-player game. And we can do that as follows. So first we need to solve this limiting analog of this ordinary differential equation that we have. So we replace the function q we had there with the one that we get by putting mu instead of mu g as this measure here. So this is the kind of new analog of our normalized determinant that we had for Q. So we solve this ODE, and then what we can say is that the law of a typical player in our n-player game is converging to a centered Gaussian with this variance V, which is determined by mu. This is the same formula from before, but now with mu in place of mu g for the variance of one typical player. Okay, so you can say a similar convergence for the value function. You can also show that the empirical measure is going to converge to the same Gaussian limit in probability. And this is kind of the more important, the more intriguing point that I want to dwell on for the rest of the talk. But this is another good place to pause for questions. This is the last main theorem I want to present that kind of explains in these explicitly solvable transitive graph cases, how do we take limits? Any questions here?
Are there any questions from the virtual audience? I don't see any chat messages. Guess not. Any questions here?
Can you say something about players which are connected with each other? The law of two players?
Yes, this is a good question. So this is something I'm going to elaborate on in this coming discussion. So okay, you can plot some things in the cycle graph case. I think I'm going to skip these slides here to get more to this question of empirical measure convergence and some interesting ideas that show up here. So again, starting with the mean field case is a benchmark. So either the complete graph case or more generally, as I just said, if the eigenvalue measure converges to a delta -1, then what you can argue is that if you take any two players, then their state processes will be asymptotically independent, with each one having the Gaussian marginal that I wrote on the previous slide. Okay, so this is the mean field case. Arbitrary players become asymptotically independent. Now, in the general case, this fails. In the case where the eigenvalue measure converges to some non-degenerate limit, this statement fails. Arbitrary players do not become asymptotically independent. But instead of arbitrary players, if you sample two uniformly random players, then these will become asymptotically independent. So uniformly random players are still asymptotically independent. And the reason is kind of interesting. So if you think, why should we need to sample uniformly at random? Why can't we work with arbitrary players? The cycle graph is a good example. If you have a larger and larger cycle and you take two guys sitting next to each other at this large round table, they're still going to be dependent even as the table grows around them. I mean, this is not a rigorous proof, but hopefully this example, you can imagine they would still be dependent if we have boundedly many neighbors and you just look at two neighbors in your network. What happens, right, so as a side note, just to connect this back to this empirical measure story, this is basically equivalent to this statement here of uniformly random players being asymptotically equivalent or independent is basically equivalent to the empirical measure concentrating around its mean. So this statement is used in the proof of the empirical measure convergence, pretty crucially. Now, so why are uniformly random players asymptotically independent? This comes from two key facts. The first is a correlation decay. So I told you that the players in equilibrium will look at everybody else in the network. But the more distant you are in the network in terms of the graph distance, the less you'll depend on each other. And this you can quantify in terms of the covariance between two players, which is decaying exponentially with respect to the graph distance between the vertices. Okay, so distant players in the network tend to be, more and more independent. So this is the ingredient number one. The second ingredient is that in a sparse graph, two randomly chosen vertices tend to be very far apart. Okay, so these are the two things behind this asymptotic independence in the sparse case. So in the dense case, the correlation decay doesn't play a role. In the dense case, what happens is that you have more and more neighbors. So the fact that the degree is diverging in the denominator here is what makes people become asymptotically independent. You have more and more neighbors to average over. But in the sparse graph case, you have asymptotic independence of random players because two randomly chosen players tend to be very far apart and because distant players tend to be approximately independent. So this is a kind of different thing driving this asymptotic independence phenomenon in the sparse case. So this is how we do things in this case. I think I have a little bit of time to comment on the proofs here, which are connecting with the theme of this longer program here, really probability and PDE working together. Okay, so if we want to do explicit solutions, it's natural to work with the PDEs that characterize the Markovian Nash equilibria for our models. So for going back to our n-player game on a transitive graph, what you can do is make the kind of usual quadratic ansatz. You posit that the value function for player I should be some quadratic form, depending on the label of player I, plus some scalar term, let's say. And this turns out to be the right ansatz for us. And if you write down this kind of n-player PDE system, there's sort of a standard process of translating your n-player game to a coupled system of n HJB equations. If you plug in this ansatz, you end up with the system of n Riccati equations that are coupled with each other. And the key observation is that all of the coupling between the players can be captured in a single kind of aggregate between all of these players. And then the process becomes a sort of fixed point, as you might imagine, where you solve for one player's matrix here in terms of this given aggregate, and then try to close the loop with a sort of fixed point argument. This is not easy in general, but it's this symmetry, it's this transitivity that kind of saves the day. So far this all works without the transitivity assumption, but with transitivity, you can exploit some symmetries of the value function. So basically, if you associate to each permutation, let's say, a matrix which permutes the coordinates of a vector according to the permutation. So this is what I call R phi, is this permutation matrix corresponding to a permutation phi. Then there's a symmetry of our value functions corresponding to each one of these permutation matrices. So you can imagine then the more permutations you have, some sort of invariant that you have to work with, the more automorphisms you have, the more structure you have to play with. So if you kind of plug this into our quadratic ansatz, the symmetry we have in our value function, which just comes from permuting the players, recognizing that the structure of everything is the same, so things should behave in the same way. If you carry this through the ansatz, you find that these matrices, these ansatz matrix and scalar terms for each of the players have to relate in a fairly rigid way because of this transitivity. So actually the scalar terms are the same for every player. Matrix terms here, these quadratic form terms, have a sort of rigid symmetry of their own. They're kind of certain diagonal terms all have to match, which turns out to be very convenient. And then lastly, you can argue a certain commutativity between this aggregate matrix and the Laplacian matrix that lets you do a lot of convenient calculations. And finally, this commutativity lets you then kind of diagonalize everything and reduce to a single scalar. This ODE system comes from the eigenvalues of this so-called aggregate matrix that I called P. So it's really the transitivity that lets you reduce everything to a one-dimensional ODE system. It's natural to imagine if you had, and so transitivity you can think of as meaning there's one class of vertices, right? Everyone kind of sees the graph in the same way, but if you imagine something like a bipartite graph where there are two kind of groups of vertices, where everyone in this group, the graph looks the same from their perspective, everyone in this group, the graph looks the same from their perspective, you can imagine maybe there would be a way to reduce it maybe to a two-dimensional ODE system instead of one-dimensional. This is speculative. We didn't look into this kind of generalization, but this is just to kind of further try to explain the role of this transitivity, the symmetry in reducing the dimension of the problem to something we can work with, the scalar ODE in this case. So I think this is a good place to wrap up. In summary, really, I would say at the heart of our approach to this linear quadratic model is this kind of spectral perspective, kind of doing all the limiting analysis in terms of this, the eigenvalues of this Laplacian matrix, which seems very powerful, but maybe limited just to linear quadratic models. Nonetheless, I think this model tells us a lot about what to expect in more general setups, in particular, what the kind of sparse, dense differences will be in terms of when you can get away with the usual mean field game approximation. But I think there's a lot more to do here. In particular, the sparse case is very intriguing. There are weird things that happen in sparse regimes, and there's not really a good anything I would call a good limiting model yet in this case, right? In the mean field case, we know how to write down this mean field game problem pretty well by now. In the, not mean field, but still this graphon case, this very dense setting that Peter was discussing before me, there's a way to write down a limiting model that's kind of self-contained. It's self-contained equilibrium problem. You can use that to reconstruct approximate equilibria for the n-player game. Now, in the sparse case, there's not really an analog of this. There's not really a good, simple, limiting model that we can use to then go back to the finite model or something like this. So far, our analysis of the limit model is all, or the sparse case is all done by really explicitly solving the n-player games and taking limits. And mean field game theory is somehow powerful, you could say, because it doesn't require you to solve the n-player games and take limits. So this is a gap, something that would be nice to understand better in this sparse case. But anyway, I think I'm out of time. So thank you for your attention. I'm happy to discuss this with you who are here this week. I'll be around. Thank you.
Are there any further questions or comments?
Thanks, Daniel. Maybe I didn't get it exactly in your talk, but it seems that the number of eigenvalues close to 0 is important for the sparse regime or not. And so in your case, I think is there some conditions that you can derive the way that your measure mu weights the mass on 0 to I don't know, like to distinguish between a sparse and a dense regime?
Right, this is a good question. I mean, the main way that we kind of distinguish that we're thinking about sparse versus dense is, is this mu degenerate? Is it a delta at -1 being the dense case or not being the sparse case? But more refined than that, I'm not sure what more can be said. I believe it's been a little while, so I hope I'm remembering this correctly, but if you say if you take a first or second order approximation of this variance, so the variance is kind of everything that kind of all of the information about the behavior is in this variance in a sense for a single player. If you differentiate twice at first order, the graph does not seem to be felt. It's only at the second order that you can see whether you're dense or sparse, if I'm remembering correctly. But I don't remember atoms at 0 or anything quite like this playing.
Because like if you have an atom at 1/2, you cannot say anything on the. We can because if you have an atom and 1/2, a lot of players have a lot of connections, so maybe we can.
I'm not sure I follow you.
Like if your dense regime is only if mu is at an atom at 1.
Right.
But the Dirac mass at 1. But for instance, if you have a Dirac mass at 3/4, your graph is like fully connected, basically. I don't know. It just seems to me that this condition can be reduced, but I don't know. I have no clue. I haven't done any computation.
Okay. Yeah, I'm not sure I'm completely understanding you, but I do think maybe we can talk more offline also. But
yeah, maybe I can also just take a related question. That's why I mean, but from the chat, Leah Popovich asks an amateur question: does the Laplacian or the random walk come in? Because this gives the distance between players and implies how much influence vertices at different distances from the typical have. Sort of what is the intuitive explanation of what the role the Laplacian is playing?
Right. So I think the simplest explanation for why the Laplacian shows up is just because that's exactly what shows up in our cost function. So this, let's say, average of your neighbors. I don't even know if this is visible. If you look at the average of the neighbors minus your current position, which is exactly what our terminal cost function is. This you can write exactly as this matrix, this Laplacian matrix L multiplying the vector x. You take the vth component and square this. So the simplest, most naive explanation for why this Laplacian is showing up is just because it is what governs our cost function. Anything that there may be something kind of maybe a more interesting story or connection with random walks on the graph, but this is something I haven't thought about so much, and I don't think I could give a a good answer to. But
Okay,
this is a good
thank you.
question.
Yes, Roland, yes, please unmute yourself and ask the question, please. Okay, is the spectrum always countable in the limit was the question.
No. So this is an interesting point that these discrete measures for finite graphs can often have continuous limits. So in the cycle graph case, for instance, the limit is continuous, this measure. It's the law of a cosine of a uniform, basically.
Yeah, I guess his question was, is it always countable in the limit, which is clearly not in the dense case. So
right.
It's always countable. Okay, you're saying it's continuous. Yeah.
Right,
So did that answer you, Roland, that in the cycle graph case, it could actually be a continuous limit?
I'm sorry, this is a very naive question, and certainly you answered this question at the end of the talk, but this is to be sure. You have no clue about a limiting model for which you would have the same equilibria in the end as the one that you found directly by taking the limit.
So I would say I have no good model. I have no good idea, let's say. I do have a clue that, okay, you could, to be clear, I believe the question is about this, what I was saying about the limit model in the sparse graph regime here at the end. I think one could write down a limit model which you can use to in a self-contained way, let's say, identify the equilibrium that I'm getting by taking limits. But that model would involve, say, countably many agents. For instance, if you take the cycle graph, then it converges in the local sense to the infinite line graph. And so you could write down an analogous model, but on an infinite graph, where the graph is the line or lattice or more complicated kinds of versions. I don't see this as a very good limiting model because this is not something very tractable, right? Like a mean field game limiting model is nice to work with because it kind of involves just one representative player solving some fixed point problem against this, measure flow representing the mean field. I don't see an infinite player model where there's really an infinity of agents competing together. I don't see that as a great that doesn't seem to me to simplify the story compared to a large finite system. So in that sense, I don't think there's a good limiting model. I think there is a limiting model that you could write down in these contexts, but it would be hard to work with. And I do wonder if there's something better you can do in these sparse cases, some kind of analogous, say, dimension reduction comparable to the mean field game, representative player perspective. So it's a more nuanced answer than this bullet point provided, I hope.
Yes, just following up on that, because of course, once you solve it, then it becomes like an interacting particle system, right? And then we have the limit theory that needs to develop. So you could look at the marginal dynamics of that.
Right. This is something I've thought about. We should discuss more.
Yeah, okay, we can discuss. But
yeah.
maybe I would let Shuang Gao had a question, and maybe that'll be the last question. Please, if you can unmute yourself and talk, please go ahead.
Thank you. Thank you for the nice presentation. I have a very trivial question. Just to verify my thought on this. So it seems like all the nodes in the vertex transitive case are indifferent from one another, both from their initial conditions, and hence I think their equilibrium cost will be homogeneous across nodes. And then the control will be homogeneous across the node. Just want to verify if my observation is correct or not.
I would completely agree with what you said. Yes, that absolutely this vertex transitive assumption means that every individual player has the same law and the same value, let's say in equilibrium. And in a sense, they all have the same control, but I would be more careful about the control, because in a way, it's not that every player has the same function of the other states as their control, right? Because your position relative to the other players influences how the other player appears in your control. So I guess the influence of player J on player I kind of depends on the distance between player I and J in the same way for every pair of players I and J. But it's a bit more subtle than to just say that all of the players have the same control, because they kind of depend on all of the other players at the same time, in a way. Does that make sense?
So just follow up on that, the control is executed locally, meaning that individual just take the information of their local neighbors, or it's taken, I think it's taken the distribution information across the.
So the control of a single player will depend in general on all of the other players' states. So I think this was, yeah, so this is hidden in this one line here, basically, where this matrix PT actually will be positive in every entry. So the control of player V will depend on all of the states of the players in the whole system, not just on the local information.
Okay, thank you very much. We're out of time, but of course we could always have more questions and comments later. So let's thank Dan once again for stepping in and giving a great talk.